Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The solar system, vast and intricate, is often defined by its planets, the magnificent giants and rocky worlds that orbit the sun. Yet hidden within the shadows of these celestial titans are the moons, lesser-known companions that each carry secrets, stories, and mysteries as profound as the planets themselves. These moons, numbering over 200 across the solar system, vary wildly in size, composition, and history, forming an astonishing diversity of worlds. Some are frozen orbs of ice, while others are volcanic powerhouses, shrouded in thick atmospheres or streaked with impact craters that whisper tales of eons past. They are the hidden worlds of our cosmic neighborhood, waiting to reveal the universe's enduring secrets. The moon of Earth, often simply called the moon, is the most familiar of all natural satellites. Its pale, cratered surface has fascinated humanity for millennia. Despite its proximity, it remains an object of profound scientific curiosity. Lunar exploration, from the Apollo missions to modern robotic surveys, has revealed a landscape sculpted by impacts and ancient volcanism. The moon's surface tells the story of the early solar system, preserving a record of bombardments that have long since vanished from Earth's geologically active crust. Beneath its gray surface lie clues to the moon's formation, likely the result of a colossal impact between a young Earth and a Mars-sized body. The moon not only influences life on Earth through tides, but also serves as a gateway for humanity's ambitions in space exploration, a stepping stone toward other distant worlds. Beyond the familiar moon, the moons of Mars present a curious contrast. Phobos and Deimos, tiny and irregularly shaped, resemble captured asteroids rather than traditional moons. Their surfaces are scarred and heavily cratered, and their origins have been the subject of intense study and debate. Phobos, orbiting so closely that it rises and sets twice each Martian day, is slowly spiraling inward toward Mars, destined to either crash into the planet or break apart to form a ring in tens of millions of years. Deimos, further out, drifts more gently, a quiet companion in the Martian sky. These moons, though small, offer insight into the processes that shape planetary systems and provide potential sites for future exploration or staging points for missions to the outer solar system. Jupiter, the gas giant, boasts a dazzling retinue of moons, some of which are small and irregular, while others are larger than planets like Mercury. The four Galilean moons, Io, Europa, Ganymede, and Callisto, stand as extraordinary worlds in their own right. Io, the most geologically active body in the solar system, is a world of fiery volcanoes where sulfurous plumes and lava flows constantly reshape its landscape. The tidal forces exerted by Jupiter and its neighboring moons generate immense internal heat, fueling Io's relentless volcanism. Europa, in contrast, is an icy moon with a smooth, reflective surface crisscrossed by dark streaks, likely fractures in a global ice shell. Beneath this icy crust lies an ocean of liquid water, kept warm by tidal heating, making Europa a prime candidate in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, possesses its own magnetic field and a complex surface of craters and ridges, revealing a rich geological history. Callisto, heavily cratered and ancient, seems frozen in time, a world that preserves the scars of countless impacts in the early solar system's violent history. Saturn, the ring giant, has moons that are equally fascinating. Titan, shrouded in a dense, orange-hued atmosphere of nitrogen and methane, is a world that mirrors Earth in many ways. Rivers, lakes, and seas of liquid hydrocarbons carve its surface, creating a dynamic environment unlike any other moon. Beneath its thick, hazy clouds, the potential for chemical processes akin to early Earth hints at possibilities for life, albeit in forms adapted to extreme conditions. Enceladus, much smaller than Titan, surprises with its icy geysers, ejecting water vapor and ice particles into space from a subsurface ocean. These plumes not only create Saturn's E-ring, but also provide direct access to subsurface materials, making Enceladus a target of immense interest for astrobiology. Other moons, such as Rhea, Dione, and Mimas, display cratered terrains and icy compositions, each telling a different story of bombardment, resurfacing, and potential internal activity. Uranus and Neptune, the ice giants, host smaller, less well-known moons, yet each holds unique wonders. Uranus's moons, including Titania, Oberon, Umbriel, Ariel, and Miranda, present heavily cratered surfaces, rift valleys, and strange patched landscapes. Miranda in particular stands out for its patchwork of cliffs and ridges, suggestive of dramatic tectonic upheaval, possibly due to past tidal interactions with Uranus. Neptune's Triton is remarkable not only for its retrograde orbit, implying capture from the Kuiper Belt, but also for its geologic activity, with geysers of nitrogen gas venting from its icy surface. Triton's active geology, extreme cold, and unique orbit make it a laboratory for understanding captured objects and the dynamics of distant planetary systems. Smaller moons, scattered across the outer solar system, continue to captivate scientists with their diversity and strangeness. Many of these irregular satellites, captured from heliocentric orbits, exhibit unusual rotations, shapes, and surface features. Some are tumbling through space chaotically, while others are locked in complex gravitational dances with their parent planets. Beyond Neptune, the dwarf planets, such as Pluto, host their own moons, like Charon, Nix, and Hydra, forming intricate systems where gravity weaves an intricate ballet. Charon, nearly half the size of Pluto, and locked in a mutual orbit, dominates Pluto's sky, creating a binary system unlike any other in the solar system. The smaller moons, irregularly shaped and distant, are relics of ancient collisions, preserving a record of the outer solar system's violent past. The moons of the solar system are more than mere companions to planets. They are dynamic, diverse, and sometimes hostile worlds, each shaped by the forces of gravity, radiation, impact, and internal heat. They reveal the processes that govern planetary formation, evolution, and interaction. Their surfaces, whether frozen, cratered, or volcanic, carry histories stretching back billions of years. Their interiors may harbor oceans, heat, or even the conditions necessary for life. Studying these moons allows scientists to understand not only the planets they orbit, but also the wider mechanisms of the solar system itself. Missions such as Galileo to Jupiter, Cassini to Saturn, and New Horizons to Pluto have opened windows into these hidden worlds, revealing landscapes and phenomena that challenge our expectations and expand our imagination. The diversity of moons in the solar system is staggering. Each planetary system carries its own cast of characters, some familiar, others almost fantastical in their alien landscapes. Jupiter alone has more than 90 known moons, and the Galilean moons, though among the largest, are just the beginning. Beyond these major satellites lie a multitude of smaller, irregular moons, captured from the early solar system or born from collisions that shattered larger bodies. These moons, often only a few kilometers across, are heavily cratered and irregularly shaped, yet they carry invaluable information about the history of the Jovian system and the processes that govern planetary satellites. Some orbit in retrograde, moving opposite to Jupiter's rotation, hinting at violent capture events, while others dance in resonant orbits, locked in gravitational rhythms that maintain their positions over billions of years. Among the Galilean moons, Europa stands as one of the most captivating. Its icy surface, etched with cracks and ridges, hints at a vast, hidden ocean beneath. The possibility of liquid water has made Europa a prime target in the search for extraterrestrial life. Scientists believe that the tidal forces exerted by Jupiter generate enough heat to maintain this subsurface ocean, keeping it from freezing solid despite the moon's distance from the sun. Beneath the ice, nutrients and energy sources might circulate, creating conditions similar in some ways to Earth's deep oceans, where life thrives around hydrothermal vents. Future missions, such as the Europa Clipper, aim to probe this enigmatic world more closely, scanning for evidence of water plumes, analyzing surface composition, and mapping the ice shell to understand its thickness and structure. The moon's potential as a habitable environment makes it one of the crown jewels of planetary exploration. Io, in contrast, presents a universe of fire and energy. Its surface is covered with hundreds of active volcanoes, some erupting lava fountains hundreds of kilometers high. The intense tidal forces from Jupiter's gravity, combined with interactions with other Galilean moons, flex and twist Io's interior, producing internal heat far greater than what would be expected from radioactive decay alone. This heat fuels continuous volcanic activity, resurfacing the moon constantly and obliterating older craters. The sulfurous plumes give Io a kaleidoscopic appearance, with yellows, reds, and browns painting a world in constant change. Studying Io allows scientists to understand tidal heating processes and extreme volcanism, providing insight into how internal energy can shape a world's surface even far from the sun's warmth. Ganymede, the largest moon in the solar system, is a world of contrasts. Its surface is a tapestry of bright regions marked with grooves and ridges, alongside older, darker terrain pockmarked with craters. Beneath its crust, it is believed that a subsurface ocean exists, perhaps sandwiched between layers of ice. This ocean may hold more water than all of Earth's oceans combined, and the existence of a magnetic field, unique among moons, suggests a complex internal structure with a molten metallic core. Callisto, in contrast, is a frozen relic, its ancient surface a record of countless impacts over billions of years. Its craters remain largely undisturbed, providing a window into the early history of the solar system and the bombardment that shaped it. Saturn's moons present another layer of wonder, each with unique geologies and mysteries. Titan's thick atmosphere, rich in nitrogen and methane, obscures a surface shaped by rivers, lakes, and seas of liquid hydrocarbons. Unlike Earth, Titan's hydrological cycle involves methane and ethane rather than water, with clouds forming, rain falling, and rivers carving channels across its icy landscape. The surface temperature, barely above -179 degrees Celsius, makes liquid water impossible on the surface, yet the presence of a subsurface ocean beneath the icy crust suggests the potential for chemical environments that could support life. Enceladus, despite its small size, is a powerhouse of intrigue. Its icy surface conceals a liquid water ocean, and geysers erupt from fissures at the South Pole, sending plumes of water vapor and ice particles into space. These plumes contain organic molecules, hinting at the possibility of life in the hidden ocean below. Enceladus demonstrates that even small worlds can harbor remarkable activity and that size does not preclude habitability. Dione, Tethys, Rhea, and Mimas offer glimpses into Saturn's varied satellite system. Mimas, often nicknamed the Death Star moon for its enormous crater, presents a stark, frozen landscape, while Dione's bright, wispy terrain reveals tectonic fractures and hints of past geological activity. Rhea, heavily cratered yet relatively bright, provides evidence of a moon whose surface preserves the ancient solar system's history. These moons, though not as dramatic as Titan or Enceladus, are laboratories of icy geology, demonstrating the complex interactions between planetary gravity, internal structure, and surface evolution. The ice giants, Uranus and Neptune, host moons that are lesser known but no less fascinating. Uranus's moons, Miranda, Ariel, Umbriel, Titania, and Oberon, display landscapes scarred by tectonic activity, massive canyons, and unusual surface patterns. Miranda in particular appears almost like a patchwork quilt, with regions of cliffs and ridges suggesting violent geological processes in the past. Its small size belies the dramatic reshaping its surface has undergone, potentially due to tidal heating or past orbital resonances. Neptune's Triton, with its retrograde orbit, is a captured object from the Kuiper Belt, yet it remains geologically active. Geysers of nitrogen gas erupt from its icy surface, driven perhaps by internal heat, revealing that even captured moons can exhibit dynamic behavior long after their capture. The smaller, irregular moons scattered across the solar system offer further intrigue. Many are remnants of collisions or captured objects from distant regions, irregular in shape and often tumbling chaotically through space. Their diverse orbits, rotations, and compositions reveal the complex gravitational dances of planetary systems and the chaotic history of the solar system's outskirts. Beyond Neptune, dwarf planets like Pluto have their own families of moons. Charon, nearly half the size of Pluto itself, is locked in a synchronous orbit with its parent, creating a binary system. Its surface features cliffs, canyons, and evidence of ancient geological processes. Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, are irregular, rapidly rotating, and likely formed from collisions, adding complexity to a system once thought to be simple. The moons of the solar system also challenge our understanding of what constitutes a world. They are not passive bodies orbiting larger planets. They are dynamic, diverse, and sometimes extreme. Some may harbor oceans beneath frozen crusts. Others are volcanic furnaces, and still others are silent witnesses to billions of years of cosmic history. They provide laboratories for understanding the fundamental processes of planetary formation, tidal interactions, and the potential for life in environments vastly different from Earth. They are reminders that the solar system is far more than its planets alone, and that hidden worlds, often overlooked, hold profound insights into the nature of our cosmic neighborhood. While the largest moons often capture the imagination, the smaller and more distant satellites hold secrets just as compelling. Jupiter's outer moons, for example, are irregular, often only a few kilometers across, and follow eccentric, inclined or retrograde orbits. Many of these are thought to be captured asteroids or fragments from ancient collisions. Their surfaces are generally dark and heavily cratered, lacking atmospheres, but they offer a record of the chaotic history of the Jovian system. These moons, though small and remote, help scientists reconstruct the dynamics of planetary formation and the sculpting of the early solar system. Even their peculiar orbital patterns tell a story of gravitational interactions, resonance effects, and the long-term evolution of planetary systems. Saturn's irregular moons provide a similar window into distant, icy processes. Many orbit far from the planet, following paths that are elongated or tilted relative to Saturn's equator. Phoebe, one of the most notable of these distant moons, is thought to be a captured object from the Kuiper Belt, bearing similarities to primitive bodies that formed in the outer solar system. Its dark surface, rich in carbon compounds, contrasts with the bright, icy inner moons. Studying Phoebe provides clues about the composition of the early solar system beyond the frost line, where temperatures were low enough for volatile compounds to condense, forming icy planetesimals that may have later contributed to the formation of giant planets and their satellites. Moving to Uranus, the outer moons are relatively small and irregular, but their geological history is intriguing. The outer satellites, such as Caliban, Sycorax, and Prospero, are distant and irregularly shaped, captured long ago by Uranus's gravitational pull. Their compositions suggest a mixture of rock and ice, reflecting the processes of the outer solar system. Despite their small size and cold frozen surfaces, these moons are essential pieces of the puzzle for understanding planetary satellite systems, particularly in regions beyond the gas giants, where gravity interacts with primordial bodies from the edge of the sun's domain. Neptune's system, though less studied, is no less fascinating. Triton, as previously noted, dominates the system, but Neptune also hosts smaller moons like Nereid, Proteus, and Larissa, each with unique characteristics. Nereid, with its highly eccentric orbit, experiences dramatic variations in distance from Neptune, creating extreme variations in gravitational stress that may influence its surface. Proteus, one of the largest irregular moons, has a heavily cratered surface with a dark, icy exterior. These moons, though distant and cold, show that the outer solar system is far from static. Even small moons experience geological processes, tidal stresses, and complex orbital interactions that shape their evolution over billions of years. Beyond Neptune, the moons of dwarf planets and trans-Neptunian objects reveal a frontier of discovery. Pluto's system, brought into stunning clarity by the New Horizons mission, includes Charon, the massive binary companion, along with smaller, irregular moons that rotate rapidly and tumble chaotically. Charon's surface shows a mixture of ancient craters, towering cliffs, and vast canyons, suggesting tectonic activity in the past. Its icy surface, composed primarily of water ice, contrasts with Pluto's more varied terrain, which includes nitrogen, methane, and carbon monoxide ices. The smaller moons, Nix, Hydra, Kerberos, and Styx, are irregularly shaped and rotate unpredictably. Likely the result of a collisional history that formed the system long ago, these satellites, orbiting far from the sun in frigid darkness, demonstrate that even the smallest worlds in the outer reaches of the solar system can be dynamically complex and geologically informative. Icy moons across the solar system hold particular fascination because of the potential for hidden oceans. Europa and Enceladus, as discussed earlier, are prime candidates for astrobiology, but other moons may harbor similar environments. Ganymede's subsurface ocean, Titan's potential liquid water beneath its thick crust, and even Callisto's hypothesized internal ocean suggest that habitable environments may be more common than previously thought. These oceans are shielded from the harsh radiation of space, warmed by tidal heating or radioactive decay, and in some cases may interact chemically with rock or ice, creating conditions that could sustain microbial life. The discovery of plumes erupting from Enceladus, containing organic compounds and water vapor, has opened the possibility of sampling these hidden oceans without drilling, a tantalizing prospect for future missions. These moons are not just frozen rocks. They are dynamic, potentially life-sustaining worlds hidden in plain sight, orbiting giant planets and dwarf worlds alike. The geology of moons is as diverse as their potential for life. Volcanism, tectonics, ice flows, and impact cratering all contribute to a rich variety of surface features. Io's constant volcanic activity reshapes its surface daily, while Europa's icy shell shifts and fractures with tidal flexing. Titan's methane rivers carve valleys and lakes, Enceladus's icy jets reveal a subsurface ocean, and Miranda's patchwork terrain hints at violent geological upheavals. Even the smallest irregular moons, once thought insignificant, show signs of impact reshaping, collisions, and orbital evolution that speak to the solar system's turbulent past. By studying these surfaces, scientists learn not only about the moons themselves, but also about the processes that shape planets, asteroid belts, and other small bodies across the cosmos. Moons also provide critical insight into planetary atmospheres and magnetospheres. For example, Jupiter's moons interact with the planet's intense magnetic field, generating auroras and electric currents that influence both the moon's and Jupiter's magnetosphere. Saturn's moons, particularly Enceladus, contribute material to Saturn's rings and magnetosphere through geysers and ice particle ejection. These interactions are not mere curiosities. They are key to understanding the dynamic relationships between moons and their parent planets, how material is exchanged in planetary systems, and how magnetic and gravitational forces sculpt the environments of both satellites and planets. From a human perspective, moons represent stepping stones into the broader solar system. The moon has already served as humanity's first foothold beyond Earth, and future exploration may extend to Mars's moons, Phobos and Deimos, serving as bases or staging points for journeys to the outer planets. Icy moons like Europa, Ganymede, and Enceladus may one day be explored directly, their subsurface oceans probed for signs of life. Titan's dense atmosphere and hydrocarbon lakes could provide unique opportunities to study chemistry unlike that on Earth. These moons are not just scientific curiosities. They are potential destinations, laboratories, and perhaps even homes in the distant future of human exploration. Among the outer reaches of the solar system, moons serve as chronicles of time, preserving records of both violent origins and delicate processes that have unfolded over billions of years. These moons vary not only in size, but in composition, surface activity, and potential for hosting life, revealing that the solar system is far more complex and alive than the distant darkness might suggest. Ganymede and Callisto, Jupiter's giant satellites, illustrate this contrast beautifully. Ganymede, with its magnetic field and grooved terrain, points to a past rich in geological activity. Evidence suggests that convection within its icy shell has produced the striking parallel ridges and valleys that crisscross the surface. Beneath, a deep ocean may exist, layered beneath ice and perhaps interfacing with a rocky mantle, where chemical interactions could provide energy sources for life. Callisto, in contrast, is almost a frozen time capsule, its cratered plains virtually unchanged for eons, offering a record of early solar system bombardments. Together, these moons show the range of outcomes that can emerge under the gravitational influence of a giant planet, from dynamic, evolving worlds to ancient, nearly inert landscapes. Jupiter's lesser-known moons, including Amalthea, Himalaya, and the irregular captured satellites, reveal further intricacies. Amalthea, for instance, is small, irregularly shaped, and coated with red dust likely derived from surface interactions and radiation exposure. Himalaya, Jupiter's largest irregular moon, exhibits a more spherical shape but remains heavily cratered, a relic of collisions in the chaotic early solar system. These moons, while diminutive and often overlooked, provide insights into capture processes, collisional history, and the gravitational sculpting of satellite systems. The study of their orbits and compositions helps scientists understand how giant planets acquire and retain their satellite families, a process that may mirror the early history of exoplanet systems throughout the galaxy. Saturn's moons illustrate an even more extraordinary spectrum of environments. Titan, with its dense nitrogen-methane atmosphere, functions almost as a second Earth. The chemistry of Titan's atmosphere and surface produces rivers, lakes, and seas of liquid hydrocarbons, primarily methane and ethane. Seasonal changes create a dynamic environment where weather patterns shift across vast dune fields and frozen plains. Beneath the surface, a global ocean of water may exist, kept from freezing, solid by tidal heating, and perhaps a layer of antifreeze-like ammonia. Titan demonstrates how moons can harbor complex chemical environments far from the sun, and it challenges our understanding of habitability, suggesting that life might emerge in conditions utterly unlike those on Earth. Enceladus, though much smaller, provides a striking counterpoint. Its south polar geysers eject water ice and organic compounds, creating Saturn's E-ring and hinting at a subsurface ocean heated by tidal forces. These features make Enceladus a prime candidate for astrobiology, where future probes could sample plumes directly, searching for molecular signatures of life in a moon no larger than 500 kilometers across. The ice giants, Uranus and Neptune, have satellites less familiar to the public, yet they are no less fascinating. Uranus's moons, including Ariel, Umbriel, Titania, Oberon, and Miranda, display landscapes that speak to violent pasts and potential internal activity. Ariel shows evidence of extensive tectonics, with ridged terrains and canyons suggesting crustal stretching, while Umbriel remains darker and more heavily cratered, a quieter world whose secrets lie beneath. Miranda, with its patchwork of ridges, cliffs, and valleys, may have experienced episodes of tidal heating or past orbital resonances that cause dramatic reshaping despite its small size. Neptune's Triton, captured from the Kuiper Belt, is geologically active, with nitrogen geysers and a surface that shows evidence of past resurfacing. Its retrograde orbit, combined with tidal interactions, indicates a complex history of capture, heating, and evolution. Triton may even possess a subsurface ocean, warmed by tidal friction, offering yet another potential habitat in the distant solar system. The moons of dwarf planets and Kuiper Belt objects provide further evidence that hidden worlds abound far from the sun. Pluto's system, unveiled in exquisite detail by New Horizons, includes Charon, its massive companion, locked in a synchronous orbit. Charon's surface features towering cliffs, canyons, and smooth plains, suggesting tectonic processes that shape the satellite long after its formation. Smaller moons, Nix, Hydra, Kerberos, and Styx, rotate chaotically, their irregular shapes hinting at collisional origins. These distant satellites, while frigid and remote, challenge assumptions that small bodies are inert or unremarkable. They preserve information about the outer solar system's formation and provide laboratories for understanding the dynamics of binary systems and the effects of collisions in shaping satellite populations. The search for life beyond Earth has focused increasingly on moons. Europa's subsurface ocean, Enceladus's icy plumes, Ganymede's hidden waters, and Titan's complex chemistry illustrate that life could exist in environments radically different from Earth's. Even small moons may host niches where chemical energy, water, and heat converge. These moons challenge our anthropocentric views of habitability, suggesting that life is not confined to the warmth of a planet's surface, but may thrive under ice, in oceans beneath frozen crusts, or within chemically active layers of rock and ice. Moons provide both potential habitats and natural laboratories to study prebiotic chemistry, tidal heating, and planetary evolution, making them invaluable targets for future exploration. Moons also play critical roles in shaping planetary systems. Tidal interactions influence rotational periods, internal heating, and orbital evolution, affecting not only the moons themselves but also their parent planets. Saturn's rings, for example, are continually replenished and sculpted by the gravitational interactions of small moons. Jupiter's Io generates electric currents in the planet's magnetosphere, creating auroras and influencing space weather around the giant planet. Even distant, irregular moons contribute to the gravitational ballet of their planetary systems, maintaining orbits through resonance and occasionally undergoing dramatic collisions or ejections. Understanding these interactions sheds light on the mechanics of satellite systems across the galaxy and helps explain how planets and moons evolve over billions of years. From a human perspective, moons represent both challenges and opportunities. The moon has already served as humanity's first foothold beyond Earth, and future exploration may extend to Mars's moons, Phobos, and Deimos, as potential bases or staging points for journeys to the outer planets. Icy moons such as Europa, Ganymede, Enceladus, and Titan could be explored through orbiters, landers, and even subsurface probes, revealing oceans, chemistry, and potential life. These moons are not merely satellites, they are stepping stones for scientific discovery, exploration, and perhaps even human expansion into the solar system. They teach us that the solar system is not a static collection of planets, but a dynamic, interwoven network of worlds, each with its own story and potential. Moons, from the familiar orbiting companions of the inner planets to the remote satellites of distant dwarf planets, are windows into the solar system's history and complexity. They preserve evidence of collisions, orbital shifts, geological activity, and the interplay of gravitational and magnetic forces. Some are ancient and unchanging, frozen in time, while others are dynamic and evolving, reshaped by internal heat and tidal forces. They host oceans beneath icy shells, volcanic landscapes of sulfur and lava, methane lakes, and atmospheres thick with nitrogen. They are laboratories for understanding planetary formation, natural satellites' evolution, and the processes that might give rise to life in extreme conditions. In studying these hidden worlds, humanity gains insight into the past, present, and future of our cosmic neighborhood, uncovering lessons that extend far beyond Earth. Beyond the major moons of the solar system lie countless smaller satellites, some so tiny and faint that they were only recently discovered. These small moons, often irregularly shaped and no more than a few kilometers across, orbit their planets in complex patterns, some in retrograde, others in elongated, eccentric orbits. They are frequently fragments of larger bodies shattered by collisions or captured asteroids from the outer reaches of the solar system. Despite their diminutive size, they play an outsized role in sculpting the environments around their parent planets. Many of Saturn's ringlets, for instance, owe their shape and structure to tiny moonlets, some of which carve gaps or shepherd the icy particles that form the intricate bands visible from Earth. Even minuscule moons like these influence planetary rings, gravitational resonances, and the orbital dynamics of larger satellites, showing that size does not determine significance in the cosmic order. Some moons are truly exotic, defying easy classification. Neptune's Nereid, with its extremely elongated orbit, undergoes dramatic changes in distance from the planet, creating tidal stresses that subtly influence its surface and internal structure. Saturn's Hyperion tumbles chaotically through space, rotating unpredictably while maintaining a sponge-like surface marked with deep craters. These irregular and unpredictable motions highlight the chaotic processes at work in the outer solar system and demonstrate that not all moons behave as neatly as the familiar spherical bodies we see around Jupiter and Saturn. Even smaller inner moons of giant planets like Metis, Adrastea, and Pan at Jupiter and Saturn are dynamically active in ways that connect directly to their parent planet's ring systems, shepherding particles and maintaining the delicate balance of these intricate structures. Comparing moons across the solar system reveals striking patterns and contrasts. Inner moons tend to be small, heavily cratered, and tidally locked, with surfaces shaped primarily by collisions and gravitational interactions. Outer moons are often captured objects, irregular in shape, and sometimes display chaotic rotations. Among the larger satellites, geological activity is closely tied to internal heating mechanisms. Tidal forces dominate in Jupiter's and Saturn's moons, while radioactive decay may contribute more significantly to smaller, rocky moons farther from giant planets. Ice-rich moons often harbor subsurface oceans or geysers, whereas rocky or metallic moons like Io exhibit extreme volcanism or molten interiors. This diversity illustrates that moons are not merely secondary objects. They are laboratories for understanding planetary science, dynamics, and the conditions that may allow life to emerge. The potential for life on moons is among the most tantalizing aspects of these hidden worlds. Europa and Enceladus offer subsurface oceans with access to energy and organic compounds, suggesting environments where microbial life could exist. Titan's complex atmosphere and surface hydrocarbon chemistry provide a radically different but potentially habitable system, demonstrating that life may thrive in conditions far removed from the Earth's familiar water-based ecosystems. Even Ganymede and Callisto may harbor water beneath their icy shells, though their thick crusts make access more challenging. These moons force scientists to expand definitions of habitability and to consider environments where life might exist in forms and conditions unimaginable on our home planet. They are not just satellites, they are potential cradles of life, frozen or hidden, waiting for exploration. From a practical standpoint, moons also represent future waypoints for human exploration. Phobos and Deimos, Mars's tiny moons, could serve as staging grounds for missions to the Martian surface, offering low-gravity platforms for spacecraft assembly or fuel production. Europa, Ganymede, and Enceladus may eventually be explored with orbiters or landers capable of probing subsurface oceans, while Titan's dense atmosphere and liquid hydrocarbon lakes present opportunities for aerial and surface exploration. Even the Moon, our closest companion, continues to offer lessons for establishing off-world bases, resource extraction, and long-term habitation. In this way, moons are both objects of scientific curiosity and practical assets for humanity's expansion into the solar system. The story of moons is also a story of cosmic history. Their surfaces preserve the scars of billions of years of collisions, tidal stretching, and volcanic activity. Their compositions record the primordial materials from which planets and satellites formed. Their interactions with magnetic fields, atmospheres, and rings illuminate the dynamics of planetary systems. Even small, irregular moons contribute to this narrative, acting as relics of the processes that shape the solar system's architecture. In studying moons, scientists can reconstruct events from the solar system's infancy, understand ongoing evolutionary processes, and anticipate the fates of planets and satellites in the far future. Moons are not merely passive companions. They are active participants in the cosmic dance of creation, destruction, and transformation. As humanity looks outward, moons provide both inspiration and opportunity. They challenge our understanding of habitability, push the boundaries of exploration, and reveal the diversity of worlds that exist within even a single planetary system. Each moon, whether a volcanic powerhouse, a frozen relic, or a tiny shepherd of rings, is a world in its own right, with unique geology, chemistry, and potential for discovery. Together, they form a network of hidden worlds that enrich our knowledge of the solar system, offering insights that could not be gained by studying planets alone. They remind us that the universe is layered, intricate, and full of surprises, with wonders lurking in places we might least expect. In conclusion, the moons of the solar system are more than mere satellites. They are windows into the history, dynamics, and potential of the cosmos. From Earth's familiar moon to the icy expanses of Europa, from volcanic Io to methane lakes of Titan, each moon contributes to a greater understanding of how planetary systems form, evolve, and sustain complexity. Small moons, irregular satellites, and distant dwarf planet companions enrich this picture, highlighting the diversity and richness of our cosmic neighborhood. Hidden worlds abound, And as exploration continues, they will reveal even more astonishing secrets. From subsurface oceans to chemical complexity, from geological marvels to potential habitats for life. These moons, quietly orbiting their planets, stand as reminders that the solar system is not simply a collection of planets orbiting a star, but a dynamic, interconnected family of worlds, each with its own story and significance.